second Julia meetup in Hungary. I'm very happy to present Gábor Szárnyas to you, who will talk to us about graphs and how they use Julia to do graph processing.
Okay, thanks Joe for the kind introduction. So welcome everyone at the second ever Hungarian Julia meetup, and in the next 30 or so minutes I will talk about how we apply Julia to solve a couple of our graph processing problems. So, as you are probably aware, graphs are everywhere. We will first review the sort of graph analytical problems that come up in the wild, and then we'll talk about a couple of specific graph metrics, such as counting triangles in a graph and determining the clustering coefficient in a given graph. Then we will check out a couple of optimizations. We'll see how we can use semi-rings for traversals in graphs, and we'll try to demonstrate the ability of Julia's matrix library, and we are also looking to get some feedback from you, the audience, about how we can improve our solutions. So first, as I said, graphs are everywhere. They are used in computer science. They are basically widely used in software engineering for tasks such as dependency management or compiling software or representing anything that has a semi-structured sort of network-like shape. And obviously other fields are no exception. In biology, in physics, and in social sciences, graphs have been used for the last 50 years to capture network-shaped data structures. There's actually a separate field founded by László Albert Barabási, which is called network science. This field deals with the analysis of large but mostly homogeneous graphs. So, as an example of a homogeneous graph, let's take a look at a social network. This is a well-known kind of graph. We can see that we have 5 people here, from Bob to Fred, and these people have various acquaintances between them. This is very interesting if we want to look at the relationships between these people, but there is more to this than that. We can actually introduce types or introduce labels on these edges. So as you can see now, we have friends. For example, Bob has 2 friends and he has 1 business partner, and this allows us to gain a better insight to the inner structure of the network. For example, we can observe that Dan is mostly connected through business relationships, and Carol is more involved in friendships with the people on the graph. So this sort of graph has many names. It's called a heterogeneous network, it's called a typed or a labeled graph, and it's also called a multiplex graph. They really come by many, many names. One common way to represent these graphs is the notion of adjacency matrices. If you have studied computer science, this is basic textbook stuff, but if you didn't, it's not that difficult. We usually abbreviate it with A for adjacency matrix, and we create an n by n matrix that has 0 if 2 nodes are connected. For example, Bob and Fred are not connected directly, so there is a 0 there, but Bob and Carol are connected, so there is a 1 there. On the bottom left, we see the untyped adjacency matrix, so it just encodes whether or not 2 nodes are connected or not. On the right column of the slide, we can see 2 matrices. The adjacency matrix for business encodes whether 2 people are in a business relationship, and analogously, the friends adjacency matrix encodes whether 2 people are friends or not. So let's take a look at a couple of classic graph metrics. The first definition that we need is the notion of a triangle. This is pretty self-explanatory. We have a node V, and the node V has 2 neighbors, and the neighbors are connected to each other. There is another notion called a wedge, which is basically like an inverse V-like shape. It means that the vertex has 2 neighbors, and the neighbors are either connected or they are not connected, so we don't know the actual state of this dashed edge. The local clustering coefficient is a metric that is determined for each node in the graph. So it's actually the ratio of the number of triangles in a given node and the number of wedges in a given node. This is a normalized value, which is at least 0 and at most 1. refinement of this metric is the so-called typed clustering coefficient. In this case, we refine the notion of the triangle so that the two edges from node V are of the same type, and the edge between the neighbors must have a different type. So for example, these are friends edges, and this is a business relationship edge. This is adapted to the wedge as well, so we require these two edges to be of the same type, and we don't add any constraint to the dashed edge. Following this, similarly to the local clustering coefficient, the type clustering coefficient is just the ratio of the triangles and the wedges in a given graph. And we can see why this is useful. If we only apply the local clustering coefficient, we get a uniform distribution of metric values, so it doesn't distinguish Bob from Carol or Dan or Fred or any other person in this social network. But if we calculate the type clustering coefficient, we get very different values. You can see that Dan has 1/2 and Carol has 2/3. So these are a better way to capture the sort of inner structure of the network and the relationships between the types. To calculate these metrics, we first need to find a way to count the triangles. It turns out that this is actually the difficult part of the problem. So once we have calculated the triangles, the rest is very easy. It just follows from the equations. But this is the sort of thing that is expensive to calculate, and this is the one that we have to get right. So to do triangle counting, we first sort of experimented with the multiplication of adjacency matrices. So if you studied computer science, you know that if you take an adjacency matrix and multiply it by itself, you get the two hop paths in the graph. Or if you take an adjacency matrix and raise it to the power of 3, so it's A times A times A, you get the triangles, you get the 3 hop paths in the graph. And if you take such a matrix and take the diagonal elements, those will be the 3 hop paths that close in the same node, so these will be the triangles. This can be adapted to typed triangles as well, which is a pretty simple formula that follows from the other one. So as I mentioned, in the untyped case, what happens is that we first calculate A times A, which is this matrix right here, and this encodes all the 2 hop paths in the graph. We then multiply it by the adjacency matrix a second time, and we get all the 3 hop paths. And then we select the diagonal elements, which are the number of triangles for each node. For the typed case, it's actually pretty simple. As I said, we just take one of the types and the other corresponding matrix for the other type, and we perform the same multiplications. We again take the diagonal elements, and we get a vector that contains the number of triangles, so we can see that this node has 6 triangles. And actually, this operation is often cheaper than for the untyped case, because these matrices are a lot more sparse than the ones for the local clustering. So in the upcoming slides, we will mostly focus on the untyped case. So we always just calculate the third power of the A adjacency matrix. So one observation that we can make is that we only use the diagonal elements of the matrix, which means that we do a lot of unnecessary calculations. We enumerate A to B to C to D, and then we do not use the resulting 3 hop path. So this is not very useful. This just introduces some redundancy and makes the matrices a lot more dense. So one of the trivial optimizations is to filter the 2 length paths with a masking operation. We, instead of calculating A times A times A, we calculate A times A and do an element-wise multiplication, and then get the sum of all the rows in the graph. We can adapt it to type clustering. This is a bit more involved, but it's very nicely written in Petra's master's thesis. So we spent a few weeks coming up with this formula, but it's actually, once you have it, it's not that difficult to program. The troubling part is actually calculating these sort of A times A element-wise multiplication A matrices. So, as I said, the implementation is a tricky part. We tried many languages and many libraries, and it turned out that this sort of matrix multiplication problem over sparse matrices is a lot more difficult than we initially thought. So we have tried a number of Java libraries, none of them actually worked, and then we tried to use the sort of approach that is traditional in high-performance computing. So we tried languages like R and Python, we created small prototypes, and then we obviously ran into performance problems. So R scaled very badly, and Python scaled okay-ish for a couple of 100,000 nodes, but it kept breaking for more than 10 million nodes. So we rewrote a couple of small algorithms in C++, and it turned out to be very quick, but it was very difficult to adjust it and adapt it to different graph metrics. So this reminded me of the traditional high-performance computing approach that must be familiar to many of you. First, just run the experiments in a so-called productivity language like Python and R, and then rewrite the whole resulting code in a performance language such as C, C++, or MATLAB if you have a fitting MATLAB library. So this isn't ideal. Just to show you the scale of the problem, I actually went on the software recommendation Stack Exchange, wrote this very lengthy question, got a couple of upvotes, and it turned out that all the libraries were very slow, either for loading, for calculating the multiplied matrices, or for both. This was the typical approach. So the sort of bottom line is there are no suitable Java libraries for this problem because it's so ill-fitted to the sort of object-oriented, garbage-collected, single-threaded approach that many Java libraries apply. So this was about the time when I discovered that Julia actually has good support for sparse matrices called sparse arrays, and it not only has support to actually just represent sparse arrays as common in Java libraries as a dictionary or as a list of lists, it actually has the proper CSC compressed sparse column format, which is very efficient to use, and it can actually initialize these compressed matrices in a reasonable amount of time, which means a couple of seconds for a matrix with a million nodes. So million by million sparse matrix can be initialized in a couple of seconds. This is an example piece of Julia code. So as you can see, if we go from the initial lines, we first do the imports, obviously, then load the data set. This is actually a Facebook-inspired data set. So they claim that this is not real Facebook data, but it actually follows the data of the Facebook graphs distribution. We then do a read delimited load process of the vertices and the edges. We then create a unique vector to create a bijective mapping from the vertices and the indexes in the adjacency matrix. Then we create a mapping. This is a sort of tricky re-indexing of the source and target arrays, which is performed very efficiently thanks to Julia's backend. And then we initialize the sparse matrix. And this is the interesting part. So this matrix has about 600,000 nodes, but it's very dense because it's a social network. It has more than 30 million non-zero values. So even something as simple as calculating A times A is pretty demanding. So it actually takes about 7 seconds to calculate this on a server machine, and it uses 65 gigabytes of memory. And the interesting thing is that it will return a matrix with about 300 million non-zero values. And the problem is that if we do just another times A, so we calculate the 3-hop path instead of the 2-hop path, it just crashes. It sort of spins the CPU for a couple of minutes and then runs out of memory. So this is the place where we applied the element-wise multiplication, which is an optimization to just count the number of triangles in a given node. And this resulted in an additional 15 seconds to finish the calculation, and it actually reduced the memory consumption at the end of the computation. So this was something, these 3 lines was something that took basically all of the Java libraries out of contention, but it worked pretty well for Julia, even though we had to utilize the sort of algorithmic optimizations, because it's just not possible to run these without applying a bit of thinking. Okay, so the next kind of graph metrics that I would like to talk about are graph traversals. It turns out that if you use adjacency matrices, many graph algorithms can be captured over custom semi-rings. These are semi-rings where you overload the multiplication and the addition operator. So real numbers is a very well-known example. Obviously, for real numbers, we use the standard arithmetic multiplication and the standard arithmetic addition, and we have already seen that this is very useful to capture something like clustering in the graph. There is another sort of semi-ring that is very useful. It's called the min plus, which turns out to be particularly useful for capturing shortest path algorithms. For example, something like Floyd-Warshall or the Bellman-Ford algorithm, if you have learned such things in algorithm class. These can be captured very efficiently with the min plus algebra. And there is also the so-called Boolean semi-ring, which uses logical AND operator for multiplication and the logical OR operation for addition. And this turns out to be useful for traversing the graphs. For example, sort of breadth-first BFS algorithm can be captured with this sort of Boolean semi-ring. This is actually a pretty new idea. So there are 2 recent books, one from 2011 and one from last year, that try to explain this idea. And even though it has been around, they have not been implemented. So if you take a random Java library or even a C library, you will not find support for this sort of custom semi-rings. So it's just not possible to describe shortest path, traversal, and other sort of algorithms. Luckily, however, we are at a Julia meetup, so there's actually a pretty simple way to define a logical OR semi-ring in Julia. So as you can see, it's basically not easy to read, but it's kind of self-explanatory. We introduce a custom addition operator, which is the logical OR. We introduce a custom multiplication, which is the logical AND. And then we define the 0 element, the 1 element, and we define how the operations should be performed. And basically that's it. I have to confess that we did not come up with this. There's actually a very nice paper titled Novel Algebras for Advanced Analytics in Julia from 2013. But it's nice to take just 25 lines and basically be done with it and just use the standard matrix multiplication operators in Julia and know that the underlying operations will be performed following this Boolean semi-ring specification. So I think this was the nicest thing that we sort of experienced when working with Julia. Once we have this, once we load this custom operator, we can actually implement the breadth-first search algorithm in a couple of lines. Basically, it creates a vector and then it starts to fill the vector with the visited elements. So it's kind of works in a similar way than the textbook implementation of BFS works, but it uses these logical OR semi-ring to mask out the nodes that were already visited, and then it uses the AND part of the semi-ring to extend the operation and add more nodes to the traversal. Okay, and finally, there is the problem of masked matrix multiplication. This has an interesting illustrative example. So this is basically an idea from the field of database management, and it was described in the context of join algorithms, but it's very easy to apply for problems in graph analysis. So this is an edge-typed graph, and we have these red, these blue, and these green edges. And the backstory is that we have these three weird groups of people, A, B, and C, and each group of people has someone like the king. But this is a very strange king, and the king doesn't talk to any of the regular people, and the regular people don't talk to each other. So this is just a crazy group of people who don't talk to each other. But the king talks to the neighboring kings, and the king talks to the regular people in the other towns. So this is a weird society. And the task that we have to compute is that we have to get the colored triangles, so the triangles that have a red, a green, and a blue edge. And the thing is that it is rather tricky, because if we do it naively, we will enumerate a number of wedges that will not close to a triangle. So we will start from all of these regular people, and we will experience that if we connect to the two kings, they will be closed. But if we connect to, let's say, this king and another regular people here, so if we do this sort of traversal, it will never close. So if there is only one king in the triangle, then it will not be actually full triangle, it will just be a wedge. And in terms of matrix multiplication, this is how it looks like. So if we take the red and the blue one, the blue type of edges, we will get a huge number of non-zero elements. This doesn't seem much, but this is actually a quadratic function of the number of people, because if we have, let's say, not 2 people but 20, this will be a 20 by 20 submatrix of the adjacency matrix. So this will be in the magnitude of the quadratic time of the number of people. The idea that we apply here is that we need to mask this operation. So we have to take a look at the actual third matrix that we perform these operations against, and we can use this idea to only determine the masked multiplication values here. So we don't have to do into all the trouble of calculating this submatrix, which, as I said, can get rather large. And this actually allows us to evaluate this in the order of magnitude of n on the power of 1.5. So this is obviously a great optimization. And this is something that's not really supported by any of the regular matrix libraries. So even though you can get things like BLAS or get things like MATLAB's optimized matrix libraries, they never do this sort of masking operations, and these make them unsuitable for these graph operations. The bad news is that, as far as we are aware, Julia doesn't offer these sort of operations. So if when we went to just Stack Overflow and Googled the issues at Julia, they stated that they do not have this feature yet, but you can go and write it for yourself. So we actually tried, and it didn't work very well, but this is partly why we're here. So we hope we can get some feedback from the audience. The idea is that we did a double nested for loop, and for each row in the matrix, we calculated the dot product for each non-zero elements. And this is just a for loop, and inside there is another for loop. So this is pretty straightforward. We extract a row, which obviously is a columnar vector, we transpose it, and we extract another columnar vector and calculate the dot product, and we try to aggregate it. And we tried a number of approaches. So we tried the threads function, threads macro in Julia, and we tried the distributed macro, which creates copies, but we couldn't get it to run with good performance so far. So this is an open problem for us, whether this can be implemented efficiently. Okay, a couple of parting thoughts. So graph processing is actually more difficult than we initially thought, because you need to use a number of complex sparse matrices. They need to be operational over various types, such as booleans, integers, floats, and etc. You have to be able to use custom semi-ring which redefines the multiplication and the addition operator. So this is itself a challenge that basically blocks 90% of the available libraries. You need to use element-wise multiplication. It would be nice to have parallel execution, and the skew is a big problem, because if you cannot use these masked matrix multiplications, it will be a lot slower. So due to the distorted nature of graphs, it will be a lot slower than actually using an intelligent solution. And it seems there is no out-of-the-box solution. So we spent months trying libraries, and none of them actually worked. Julia seems a good fit between giving enough flexibility and providing good performance for our use case. A couple of lessons that we learned while we coded these algorithms is that Julia is pretty intuitive and easy to program, especially if you are used to this Fortran-esque syntax that is sometimes used in Julia. It has great performance compared to other libraries, so it's almost on par with the C++ solutions. It has good IDE support. We had no complaints with the Juno Atom plugin. And it's an evolving language, so they really don't care about backwards compatibility as far as we can tell. So we often found version 0 point something tutorials which were completely useless for example, for 1.0. They just renamed the parallel macro to add distributed, and they made a couple of changes along the way. But we could deal with these one by one. Another issue is that the error messages are sometimes difficult to comprehend. So if there is a type mismatch, it's usually just a garbled message, and somewhere in the text there is some type that should be another type, and it should be an integer 8 and not a boolean, and things like that. So these are a challenge because of the dynamic nature of Julia, but obviously this is a trade-off that we have to take. And also we found that there are no definitive answers in terms of performance, so most forums and exchange sites often just stated that if you want to know whether it's best to use a comprehension or a for loop or a map for a given problem, just do your own micro benchmarks and then see whether your use case or data distribution or type of operations can be performed quicker one way or the other. And finally, we opened the cheat sheet page. So we have these sort of cheat sheet GitHub wiki at our research group. If you look here, we have everything from Clojure through IntelliJ through Jenkins, and now Julia is in the mix. We found that it's pretty difficult to get up-to-date tutorials that are comprehensive enough to use. And we also found that there is no official Linux package, so we just use the ASDF package manager, and this basically did the trick for installing to Ubuntu systems. So this is all I wanted to say, and if you have any questions, please raise them. Thanks. Yes?
Seems like you would benefit from special kinds of caching solutions.
Yep.
Have you looked into that?
No. So the question was whether we have looked into special kinds of caching solutions. Which ones do you have in mind?
Nothing specific, but in terms of sparse matrices, I think that you could do some optimizations on memory systems, for example.
Yeah.
Calculate some parts, then some other parts, etc.
Yeah, we could do some regional grouping. The thing about sparse matrices is that one of the developers of the Scala sparse matrix library said that there is actually no such thing as a sparse matrix because they come in so many distributions and shapes that you need different algorithms. And this might be a good place to do some domain-specific caching. Yeah, so that's a good idea.
Another thing,
Okay.
on the triangle,
Yeah.
on the plus one calculation formulas, what was that inverse over the diag thing?
This is just notation, so it's diag over -1 is, from what I understand, the notation for this operation. So if you invoke diag and give it a vector like this, it will turn it into a matrix such as this, but obviously with zeros in the lower and the upper triangles. And diag -1 is just this direction of the operation. It's not a nice syntax, but it's actually difficult to express this in terms of multiplications. So that's why we use diag -1. Okay. Any feedback from Julia developers? Questions?
Question.
Okay.
Did you try GPU programming or GPU programming within Julia?
We have read a couple of papers, and one anecdote that I particularly liked is that someone implemented a BFS, so breadth first search in CUDA, and he was an experienced developer at the University of California, Davis, and it took him 8 weeks to implement the BFS algorithm on top of a GPU. So, and this was in 2013 or 15, and since then they have a whole research group that is working on creating higher level abstractions on top of GPUs, but all of these have severe limitations. So for example, this library, which is called Gunrock, which is apparently the Muppet of that university. So this Gunrock library at UC Davis actually works very well. It just doesn't support float values. So you cannot do something like a division between two values because it's only for integers. So someone before this session asked me whether Julia has any support for GPUs. So is it possible to just say add GPU and then move the matrix to the GPU and multiply it on the GPU?
I have a blog post or tutorial bookmarked about how to use a GPU with Julia, but it's quite long and haven't read it, but from that I would guess that there is no at GPU.
Okay, but there is sort of
There's
people wish.
There's like a Julia way to add CUDA kernels
Okay.
really easily. Say if you write a CUDA kernel running two arrays, it can also add matrices and n-dimensional stuff, and also it's quite comfortable, but mostly syntactically sure.
Yeah, one thing I found is that GPUs are really cut out for dense matrices. So that's why they are so good at machine learning, because it's usually dense matrix multiplication, and they are very efficient at that. But for the sparse, sort of skewed distribution matrices, they usually just run, so they start on many cores, and then one of the sub matrices turns out to be a lot more dense, and then it's just one core doing all the heavy lifting and n-1 cores running in idle. So it's not a natural fit. That's why it took this guy 8 weeks to write BFS, because you have to use some specialized load balancing to keep all the cores occupied. So that's the idea. Yes.
Another question. Do you have any high-level application for this, like use case, or like you wanted to check how people use Facebook or something like this, or is it purely for a mathematical interest?
We actually have a larger scheme research project that targets the synthesis of graphs. So think of it as creating counterfeit money, just taking the US dollar and then copying every possible sort of features and every characteristics of the US dollar. But you don't know how it's actually made. So this is what we do for graphs. We take graphs in the wild, like social networks and graphs of system models and so on, and we try to understand how they emerged, and we try to replicate this with another set of algorithms. So the idea is that you can understand at reasonable level how a graph looks like once it's built, and then you can use that knowledge to regenerate a similar graph using things like genetic algorithms or graph solvers and so on. But this is all very preliminary. But this is one of the key applications of this research. And obviously the problem is that I have a couple of backup slides for that. So the trouble is that we have graphs that are so big that it's just not possible to evaluate them. So we have a paper accepted at the WWW conference, which is the annual World Wide Web conference, and we studied their graphs with a great number of edges. Let's say this biological data set has 1.4 billion triples. Most of them represent an actual edge. So in order to calculate something as simple as a triangle count over this graph needs some serious tinkering. So we managed to get it sort of to this level. So about 50 million edges is, I think, reasonable, or 100 million edges is reasonable. But because none of the algorithms are linear, jumping to, let's say, 1 billion edges is a big issue. And we haven't yet given up on using the exact methods, but I believe at some point we will, and then we will just say, okay, we just sample the graph and then do some approximations. But I would really like to use the exact methods, because there is just no way to correctly sample a graph. And then you will get your paper rejected, because the reviewer will say that this is not a correct way of sampling, and why didn't you just calculate all pairs shortest path in this graph, which can happen. Okay. Any other questions? Yeah.
Isn't more complex structures probably more meaningful in graphs? Like you are searching for triangles.
Yeah.
Triangles very simple.
Yeah.
I'm sure there are billions and billions of triangles in every data set of that, but I don't know what meaning it has. But perhaps a more complex graph, like a graph of a molecule in a biological, that's an exact bigger molecule, that can have a meaning actually.
Yeah.
And that will be way rarer.
Yeah, so the problem with triangles is that even if we go through all this trouble of counting triangles, there are some graphs that do not have any triangle at all. So if you just take a, what's the English name? It's the bipartite graph. When you have two partitions, like you have partition A and partition B, and edges can only run between these partitions, it's very easy to see that there are no triangles in such a graph. And for these sort of use cases, we need to generalize the notion of a triangle further, and there is actually something called the K clustering coefficient, which checks for paths that have a length of K. Let's say K equals 3 gives back the triangular case, and K equals 4 gives a 4-length path, and these should be closed to the same node. And the trouble is that if we start to adapt this to the typed versions, it sort of explodes combinatorially. So it's sort of, we're back to subgraph isomorphism, which is NP complete, and it's not a nice thing to have if you have data of this scale. Okay, so that was another.
I just wanted to ask about the lesson learned page. They are still hold. I mean, didn't they say backwards compatibility on? They promised something like that. It is still a missing feature.
My opinion, as a sort of rookie Julia user, is that it's no longer such an issue because they reached stable, but there are a lot of leftover tutorials on the internet and a lot of abandoned code, which would be great if you could just do a GitHub code search and then copy-paste code from someone's repository, but it's not very simple. Still better than Python, I guess, because it's just, there is just one canonical version now. Is that? Yeah, that's correct. Okay. Okay, so thanks everyone for attending, and I think there is a social event here, so we have more beers and more pizza. Thanks.